Hi guys, today I'm going to review with you the idea behind isotopes and average atomic mass. It's been a while since we talked about this, so I just want to make sure that we recall all the important things that we can figure out just by looking at the periodic table and how we can understand how isotopes influence what the average atomic mass for any given element is. So from a definition standpoint, remember that we said that isotopes are atoms of the same element that have different numbers of neutrons, resulting in different mass numbers. So on the screen right here, just taking a quick look at this, I've chosen chlorine as my example element. You'll notice that there is a number right here, 35, and we also see it following the name of the element. And then on the opposite side, we have 37 also following the name. Whenever you see that number following the name of an element, remember that that is referring to the mass number for that particular isotope of that element. So you do need to pay attention to that because that's the number that you want to use when you're calculating your number of neutrons. Please remember that the number of protons is always going to be the same. If you take a look at your periodic table and you find chlorine on the periodic table, you're going to see that it's atomic number 17. That 17, remember, we can calculate the number of protons and the number of electrons from the atomic number 17, and in a free or uncombined element, that's always going to be the same. But in order to calculate the number of neutrons, we need to take the given mass number for whatever isotope. So if you see the 35, you're going to use 35, subtract 17, and you'll get 18 neutrons for that form of chlorine. And then if you see the 37, you're going to take the 37, subtract the 17, and you're going to get the 20 neutrons for that isotope. If you don't see a number, if all you have is the element's name, then you want to default to whatever's on your periodic table, take that average atomic mass, round it to the nearest whole number, which is the mass number, and then use that value. And for chlorine, you're going to find that chlorine 35 happens to be that most commonly occurring isotope. And so if the number didn't appear, we would use the number 35. Another thing on this slide that I would like you to just kind of take a quick look at is noticing we've got the protons and neutrons. There's so many in there that we can't sit and individually count them right now, but you'll see that the red ones represent the protons and the blue ones represent the neutrons. They are tucked into the nucleus. A lot of times we'll just use a letter to designate that when we do our atomic diagrams. You've got the Bohr models for both of these isotopes of chlorine, 2 in that very first energy level, 8 max in that second energy level, and for the third energy level, there are 7. Notice that there is no change on the number of electrons because it's still chlorine. And because it's chlorine, it has 17 protons and 17 electrons. So on this next slide, I've just used another great isotope example. This happens to be hydrogen. Hydrogen, of course, is that smallest element on the periodic table, the one with the lowest mass and the lowest atomic number. Notice there are 3 actual forms. In the most commonly occurring form of hydrogen, hydrogen 1, notice that there's no neutron. That's sort of an unusual thing that you haven't seen before. We would know that easily by taking the mass number for hydrogen on our periodic table, which is 1.01. We subtract the atomic number for the number of protons, which is 1, and we realize that that rounded mass number, of course, is 1. And if you subtract 1, you get 0. There are no neutrons in that most commonly occurring form of hydrogen. However, in this form of hydrogen, there is a neutron, so 1 plus 1 equals hydrogen 2. This is a special form of hydrogen known as deuterium. Sometimes, um, we might call it heavy hydrogen, and we might also make the same reference to tritium. When we get into nuclear reactions, we'll probably talk a little bit more about the influences of these greater numbers of neutrons in a relatively small space and what that does to the nucleus. It results in something that we call instability, but we're not going to move into that at this time. The other thing I want you to notice is that because we have atomic number 1, we still have 1 electron, and so the number of protons and electrons is identical in all 3 of the forms of hydrogen here. The only thing that's different is the number of neutrons, and therefore they have different mass numbers. One more example, and this is one that is also important. I mentioned this one when discussing it in class. Carbon. Carbon has multiple isotopes, and again, really important isotopes. The thing that I like about this slide is it does show you the relative percentage. The reason that when we look at that periodic table, we see 12.01 with carbon is because nearly 99% of all carbon in the universe is that form that has 6 protons and 6 neutrons in the nucleus. Notice here we're just looking at the nucleus. We're ignoring the energy levels. Not to say they're not important, but when we're talking about isotopes, we're really focusing on the nucleus, and that's where the difference is. And carbon-13 has 6 protons and 7 neutrons. And then carbon-14 has 6 protons and 8 neutrons. Carbon-14 is that one that I mentioned to you that is often used in radioactive dating of fossils because carbon is an element found in every single living thing. And there is always a percentage of radioactive carbon in those living things. And by using the reference value for a particular organism and comparing it to that known expected value, that's how we can date fossils. And we'll talk more about that when we get into radioactivity. But you'll notice we have 3 forms and 3 different mass numbers. All right, that explains isotopes.